So I now want to talk about state value functions. So state value is the expected future reward g of t at a given state. And that's written like this in terms of a particular policy. So we care about what the actual policy is because that's going to affect the value of a state. But it's just the expected future reward at that state. And that's true for all of the states. So we can put in this expression for future reward in terms of discounted future reward. And the idea here is that we multiply successive steps into the future where we get reward by a factor which is between 0 and 1 raised to the power of the following step. In this way that we can actually reduce the effect of being further into the future, having such a big effect on what we're doing. And secondly, it means that this series is going to converge even if the task never actually gets to a goal. So we can rewrite then the expression for value under a policy pi for state S as the expected value of all of these discounted future reward terms. And we can actually then rewrite that as well in terms of a recursive relationship, because if you notice, first of all, we can say, well, we can see that the first term here is g of t here is given by the first term plus effectively this gamma factor multiplied by the future reward at the next step forward in time. So we can substitute that into our expression for the value at state S, and we can then split this up into two terms. And we see, first of all, we have the, if you like, the immediate future reward expectation, and here we have the discounted future reward from that point onwards. Now we can first of all start writing these things down as values functions. We see that this is the expected value of this scaled version of future reward at gt plus 1, and we can see that this term here is actually the value function, right? So this is the expected value of the future reward at step t plus 1 for state being in state S is just the value function at s t plus 1, right? So we can write that everything down once again, and we have the value function here, and we have the value function here, and then we've just got this expected version of the actual immediate reward here in the middle. So given that we've got this formula, we can also slightly change how this is written, because we notice if we look at this second term here on the right hand side, we could take the expected value of a value function, and that will also still be the value function, and that's just caused iterative expectations. So because of that, we can then basically take the expected operator outside and put both terms within it, leading to this expression here. So we've got the expected value of our t plus 1 plus this gamma times value function at s t plus 1 for state equals s. So this expression here, let's just ignore that for the time being. We can see this is made up of two sums, right? So if we see the first bit here is the expected value then of the reward at the next step, and this is then the expected value of the discounted future reward. So broken down a little bit more clearly then, we see that this corresponds then to all future rewards from this state S. This is then the expected immediate reward, that's the next thing coming along from state S, and then this is the expected future reward coming along from state S. Looking at the right hand term, how can we actually evaluate this? And this is basically done bearing in mind how we calculate expectations. So if we got a value x, which is associated with a probability, I should say a value xi, because there's going to be multiple values of this, associated with a probability of xi, then we can calculate the expectation of x by summing across the product of each value with the probability it occurs at. So we can do that for this expression up here and start putting in the probabilities these things occur multiplied by their values. And what we have to do that is we have to sum across all possible actions and all possible return states. And the expression we'll end up with is of this form, and the reason we're writing it in this way is because these are the things that we actually want to use. So pi a of s is going to be the policy specification of stochastic policy. So in other words, this gives you the probability of action A given state S, and this term here gives you the probability of the next state and the reward given the current state and the action, and R is the current reward. So you can see that this is the reward term now that we care about, because we want to know the expected value of the reward at the next step. And then these terms here are just summing across these probabilities in order to marginalise those things out. So we end up with the expected value at state st equals s. And we do exactly the same thing for this second expression here. This time, again, we have to sum across all probabilities of the action given the state, multiplied by the sum across all future states and all rewards. Again, this is actually the transition function. We have our discount term here, our gamma, and we've got the value here. The value function here goes in at the end here. Okay. So overall, then, this leads to the following sum, which is, it looks quite complicated. And if we actually factorise out the expression for the policy, pi a given s, we end up with the expression the value of a state S under a policy pi is given by, first of all, the product with the sum of policy A given S multiplied by the sum across all future states and all future rewards of the probability of this thing actually occurring, multiplied by the value of the immediate reward added on the value of the future state. So we can also slightly marginalise this out a bit further as well if we wish. If we want to lose the R term here, so we don't have to sum across R, rather than having the full representation here of a transition matrix, in fact, what we can do is we can say we're going to marginalise out R, so we lose the R from this joint probability and we end up with just S prime in this term here. So this is then, if you like, the simplest form of the value function of state S. And again, it's in terms of a sum across all actions from what we know is going to be the policy that we care about, and then this is then the sum across all future states from what we know is the transition probability, and then this is the immediate reward, and this is the future predicted reward. And both of these are used. So this expression is an expected value, right? And it's just the sum, really. It's just a sum across four variables in the way we've written it here. It's a sum across all A's, all future actions. Well, it's of, obviously, current action S, and also of rewards. Like I said, pi A of S is the probability of action A given the state S, so that's the policy. And this P S prime R given S and A is the probability of the state. It's the joint probability of the next state and reward given the current state and the action. And we calculate this joint probability and then weight the reward value by this joint probability, and then basically just sum across all possibilities to get the expected value. So here's the overall anatomy then of the Bellman equation, which is the state value function for a policy pi. The state value at state S, that's what this is. This is saying the state value at state S under policy pi, that's what this is meaning, is basically found by summing across all actions using the policy multiplied by the sum across all next actions and rewards given the transition matrix, which is the probability of the next state and reward given the current state and action we take, this is the reward term, this is the discount factor, and this is the state value basically at the next state.